kick off today's session, I'd just like to take this time to acknowledge the traditional lands which we're all coming from today. I'm here on the beautiful lands of the Gadigal of the people of the Aurora Nation, and I'd like to pay my respects to the elders past, present and future. So I am so excited to have Richard Lilly joining us today. Richard is the program leader and co-founder of the National Exploration Undercover School at the University of Adelaide, and he coordinates a range of applied economic geology research projects for companies including Oz Minerals and Mount Isa Mines. And this is going to be a good one as Richard discusses the hotly debated Mount Isa story. So it's going to be a really great session. I hope you all enjoy it. Please use the chat. We'll open up the floor and have some friendly discussions at the end. And yes, thank you so much, Richard, for joining. It's wonderful having you.
I guess to start as well, I should acknowledge the Ghana people where I'm standing in South Australia, but also the Kalkadoon people of Mount Isa area, which I'm going to talk about. Thanks very much for inviting me to give this talk, Jess. It's been, I guess, Mount Isa's quite close to my heart. I lived in Mount Isa for about 8 years after moving out to Australia. And well, look, when I started at university, I learned the Mount Isa ore deposit. You know, in the UK, we learnt about it. And I guess it's always striking to see such a giant ore body. It is a very globally significant ore body. It's been one of the great providers of income for Queensland for a long time. And I guess this is such a big story. I'm not going to try and cover everything today. I'm really just going to try and introduce some of the rocks because people that know me know that I quite like looking at rocks. We'll look at the rocks and the ore textures, and we'll look at how the ideas about how this giant deposit formed, and we'll also sort of maybe look at a few of the ideas in that sense. So, as an introduction, I mean, this is a big topic. You know, we're talking about fascinating Paleozoic geology, beautiful rocks. It's globally significant mineralization, one of the great ore bodies of the world. So I'm getting a bit of noise in my headphones there. We've got the history of mining in far northwest Queensland. There wouldn't be a lot of people in this part of the world. It's pretty hot without this mine, which is a focal point for a community. And we've got the social evolution of a city as well, city of around 18 to 25,000 people, depending on what year. And of course, we have a history of changing academic opinion on this deposit. And I think we should remember as well, geology is a pretty young discipline, and ore deposit geology younger still. So I think, you know, it always is good to keep an open mind on these things. But also this mine is a modern mine, so we are going right into the future. I would highly recommend Jeff Blaney's beautiful book, Mines of the Spinifex, if you're interested in the social and sort of human aspects of the mining, not so much of the geology, but it's a great book. And this talk should really be called An Introduction to the Mount Isa geology story, because we've got a lot to cover here. I actually have a one-day workshop where we just talk about Mount Isa. And of course, there's been hundreds, probably thousands of geoscientists who have contributed to the evolution of the geological ideas concerning Mount Isa and Cloncurry. All of the errors in this are my own. And I guess as a disclaimer, this is my talk. I put this together while I was working for Mount Isa Mines, but this is not like the official line or anything. This is just a discussion, a story. And of course, it's interesting how, you know, you put 10 geologists in a room and you'll have 20 ideas or 11 ways of doing things. So it's, you know, it is very interesting case study for how we change our ideas about how things form. I'm certainly not trying to answer all the questions today. I'm going to skip over large parts that some of you may feel are really, really vital. And, you know, if we need a follow-up, more than happy to do it. And I really just want to introduce the story. And I guess I'm not trying to change anyone's minds. I learned a while ago that there's no point doing that. Once people have a fixed idea of things, it's very hard to change. You know, we'll just see how we go. I just like talking about this deposit. And of course, acknowledgements. I think before I go any further, acknowledgements to people like Roger Taylor, Bill Perkins, my student Brad Cave, who's done a lot of the work that we might dip into a little bit later on, people like Phil Reiger, who have done a lot of work in recent years, and there's a lot of papers out there on Mount Isa, too many to mention. So we're not going to go into too much academic side. We're just going to look at some rocks, tell a story. So where are we? For those of you who are joining us not from Australia, Mount Isa's about 1,000 kilometres inland from Townsville. I checked the weather today. It doesn't generally get much under 30 degrees even through the winter, so it's a pretty warm part of the world. And why do we care? Well, the Northwest Minerals province of Mount Isa and Cloncurry is one of the world's most significant metallogenic provinces. It's a source of a lot of income, obviously, but generally speaking, we can split it down the middle. We have the eastern succession around Cloncurry, which is copper gold mines, sort of IOCG. And then in the western succession, we tend to have these sediment hosted deposits. And really, with those deposits there, including Mount Isa Mines, George Fisher, Century, MacArthur River and Cannington, we're looking at most of the world's lead zinc reserves. There are plenty of other ones, but this is where most of the ore is coming from, and these deposits have got a long mine life, so we'll be mining up here for a long time. Now, I guess in this talk, I'm not going to talk about MacArthur River. I'm not going to make assumptions that what happens in one place happens in another. I think we do a lot of that, and I actually think there's best part of 1,000 kilometers between MacArthur River and Mount Isa. So I'm not going to assume that any of this applies there. I'm really just going to talk about Mount Isa and a little bit about George Fisher. So we are in Paleozoic rocks. The host rocks of the Mount Isa and George Fisher deposits are the Urcat Shale. This is the most important sort of rock that we'll really talk about. They're about 1650, 1660. They're sort of shallow marine lake sequences. They've got calc, they've got primary carbonate in them. They've got carbonaceous, there's a bit of graphite in there. So anything from, I've even seen desiccation cracks. So this was a sort of edge of the lake, edge of the sea kind of thing. There were several deformation events. I'm not going to go into them too much, but we had a sort of a rift and drift kind of stage, but basin inversion started around 1610. Then we had sort of peak, then we had sort of D1 around 1610, D2 around 1550, 1560, and then the sort of the D3, which is the transtensional, was probably around 1515 through to possibly even 1480. There's quite a few ages out there on it, but around 1500. We'll zoom in a bit. Everything in Mount Isa has this very strong north-south grain. That's from peak D2 crushing together. It's quite handy, all the hills in Mount Isa go north to south. So if you're walking home from the Buffs Club or the Irish, then you know which way to go. We'll take a cross-section roughly through the town, and you can see straight away we've got sort of the basement of Eastern Creek volcanics and a bunch of other sediments, and the Mount Isa group of sediments, which I won't really go into, but other units associated with the Urcat Shale. Now, the Mount Isa ore bodies, you'll see they sit on the Peru fault and associated with the Mount Isa fault. Now, the really significant thing here, and it's something I'd never seen before I started working there, the Peru fault is folded. It's a folded fault. So straight away, you just got to go, well, that's a bit weird. Why are we talking about a folded fault? And of course, Mount Isa is strata-bound or stratiform lead zinc with a breccia-hosted copper. And we'll look at those rocks and we'll look at the sort of discussions around it. If you take a cross-section through the northern mining area, and this is an older one, probably one of Bill Perkins, we can see our greenstone basement, quite altered, quite a lot of silicification in that basement. The yellow outline is what we call the Silica Dolomite halo, and note that it does extend into the adjacent Kennedy Spear silt zone. And our red blocks here are the lead zinc ore bodies, sort of following where the dip of the Urcat Shale, and these sort of bright greens are the copper ore bodies. You'll notice the copper ore bodies tend to be associated with either the basement contact or can be perched up in the Silica Dolomite, but you don't get much copper outside of that Silica Dolomite. That's quite an important point. But also important is you don't get much lead. Well, you do actually get lead zinc within it, but we'll get into that. This is another one of Bill Perkins' cross sections, just showing the complexity. But it's important to note, I think, that a lot of these faults, with the exception of the Peru, which disappears down and we don't know where it goes, a lot of very vertical or subvertical structures here. So you can imagine fluid flow. There's plenty of opportunity for fluids to flow around here. And zooming into that there, we'll just keep moving. So that's an aerial photo of Mount Isa. That's what it looks like from the plane landing or taking off. For those of you who haven't been to Mount Isa or live there, there's 3 stacks. We sort of used to do these ones in Mount Isa. It's sort of like big stack, little stack, and even smaller stack. So you've got the lead stack, the copper stack, and the sulfuric acid plant. And of course, they go from ore to metal in Mount Isa. The lead zinc gets refined on site and then shipped off to be fully refined, and then the copper gets sent to Townsville for further refining. We're very lucky in Mount Isa. The wind always seems to blow to the northwest 99% of the time. So they've been able to build the town quite close, and there's the town pool just a few hundred yards from the smelter. My house is just off the screen there. And just going to point out at the back here, that is the tailings for dam, out of sight, out of mind, behind Mount Isa. Now, Mount Isa's got a lot of pyrite in it, and a lot of that pyrite is quite cobaltiferous. It's quite a lot of cobalt in the pyrite, and they've been putting cobalt-bearing pyrite in there for a long time. So I suspect that is a very, very large cobalt deposit sitting there waiting for someone to work out how to process it. Just thought I'd throw that one in there. So if we take a cross-section, this is a north-south section cutting straight down the railway line. It's a bit of a cartoon, but Mount Isa, it's not a competition, but Mount Isa likes to claim that it has the most underground development in the world. I'm sure people at Olympic Dam will start sort of fighting us for that one sooner or later, but Mount Isa has been mining for a long time. And as you'll see, they've obviously started in the northern area, and sort of where the lead zinc is sort of closer to the current surface, and the copper ore bodies are relatively deep. We'll look in more detail at this later on. So if we take a section across the sort of southern area through the 1100 ore body, which is one of the world's great copper ore bodies, we have this sort of huge amount of chalcopyrite in the system, mostly contained within the silica dolomite, and not so much lead zinc. And in the north, there's sort of a bit more of, generally speaking, there's more lead zinc in the north. However, it's worth noting that the 1100 ore body was discovered by a couple of drill holes coming from the top, looking for the extension, and then it was sort of drilled out and mined from underground. They just extended the mine to the south. There's actually not been a huge amount of drilling in this area. So to say that the lead zinc is not present in the south is not necessarily correct. There's more lead zinc in the northern part of the mine, but there's definitely plenty of lead zinc through here, probably more than your average lead zinc mine. Here are some shells that Brad Cave put together a few years ago. You can see the 2% shell for copper here. You can see how it's sort of resting, almost cradled in that folded Peru fault surface, which is always generally modeled as being very flat and smooth. But I think, you know, more modern work's actually showing it's rather chopped up. There is some sort of relatively late faulting along that full of quartz and things, which has sort of dislocated a few of the ore bodies, not hugely, but maybe. And then, of course, we can chase down the 3000, 3500 ore bodies. They keep exploring further along those, and those do continue a fair bit. And of course, I just mentioned about the fact the lead zinc isn't necessarily not there. We just not necessarily done a huge amount of drilling in that zone. Here's another view, and I guess the estimate of total economic production from Mount Isa, which is coming up to 100 years of being around, discovered in 1923, which we'll get to later. You know, these are pretty big numbers, but I think given the context of modern mining, it's that grade which is really getting to, you know, Mount Isa tends to be well over 1% when they're in, well, you know, some of the stopes I've seen have just been pretty much solid chalcopyrite. So we're talking really quite a high grade copper system here. I'm not a structural geologist. I wish I was. I'm not that clever. But this is the top-down bird's eye view plan of the stopes in Mount Isa from sort of 15 years ago or so. And when you look at that in context of sort of structures and just put a few dotted lines on, it's pretty clear. We've got this rather strong structural control to the copper ore bodies. Definitely worth noting that a lot of the lead zinc also follows similar structures, which we'll come back to. But there's clearly these beautiful dilations. I mean, you couldn't pick a more classic example of sort of dilations. And as you can see, the mining environments become a little bit more challenging. Stopes get a bit smaller when you get to the points of these, but it's fairly obvious where you'd look to extend these things. Mount Isa is a zoned deposit. Regardless of how you think it formed or how we think it formed, it's zoned. It goes from more copper rich nearer the basement fault, and it zones through a sort of transition interface where you have lead and zinc turning up, and then you end up in sort of more zinc. The easiest explanation for why things are zoned is temperature. You need to keep fluids to carry copper need to be hotter than fluids to carry zinc. You can actually keep zinc in solution a lot longer, and likewise lead's somewhere in the middle. So the temperature zonation of Mount Isa is pretty clear. We will look in detail at some of these rocks. It is worth noting, though, that in the past, a lot of work on the lead zinc was done at near surface environments, or shallow, sort of in modern day terms, and a lot of the copper work was done from underground. So you've got quite a lot of research up here and quite a lot of research up here, and there's quite a big transition zone. And that hasn't necessarily been in the mine, you know, you haven't really necessarily been able to access it based on where the mine's mining. So it's worth noting that this transition zone has not been as well studied as perhaps the lead zinc system and the copper system per se each. So when you actually start looking at that boundary, that actually gets really interesting. So we're going to take a bit of a trip now through some rocks, which is my favorite thing to do. I'll briefly mention some of Brad Cave's work. I'm not going to go into the details of the geochemistry, but Brad published a paper there. It's open file. You can all access it. You can explain the temperature. You can explain the mineralogical zonation of Mount Isa from about a 50-degree temperature change. So we'll look at methods of formation, but just to say that you can do what happens at Mount Isa with about a 50-degree transition. And actually that paper's got a great summary of previous work in it. So if you ever read one paper about Mount Isa, I'd recommend that one in or Geology Reviews from 2020. So what do the rocks look like? This is classic silica dolomite. So you've got basically got dolomite here, which is that coarse white material, busted over by this grey material, which then in turn has been busted over by the chalcopyrite here, because it's quite clearly following previous fracture networks. A little bit of alteration in the black shale here, but not a huge amount. A little bit of silica dolomite alteration to black shale as well. So that's classic sort of silica dolomite down near the fault. This is another lovely example. And I guess I haven't cherry picked these pictures particularly. These are just probably the nicer pictures, but I've got thousands of pictures that all show the same sort of thing. These are very repeatable textures in the system. Here we go again. There's some dolomite. This is probably silica. There are a couple of other carbonates involved, but I'm not going to talk about the carbonate story. But it is interesting. Phil Reiger's done some great work at George Fisher picking the different carbonates with their rare earth patterns. And fortunately here down at Adelaide, we actually date calcite now. So we're getting some fantastic data on that. Here, obviously, we have our beautiful chalcopyrite, all very much infilling, some not so much alteration in this image, bit of pyrite just here. So chalcopyrite and pyrite hang around a great deal with each other in this system. Definitely worth noting that even in the most copper-rich part of the system, there is still sphalerite and galena hanging around with the chalcopyrite. It's unusual to look at a thin section and not have a little bit of chalcopyrite, a little bit of galena and sphalerite hanging around. And it's also worth bearing in mind that that chalcopyrite is really quite argentiferous. It's got a lot of, or Argentine, I should say, there's a lot of silver in the chalcopyrite at Mount Isa. And it's occurring in the crystal lattice. It's not fragments of tetrahedrite or anything. It's actually in the chalcopyrite, which I think is quite interesting. So yeah, a lot of silver in that chalcopyrite. Here's a nice one. I actually use this one when I'm teaching to show overprinting. Here we have our deformed shale. That shale looks fairly unhappy, probably some graphite bits in there, a little bit of pyrite. We won't talk about the pyrite story much today, but there is some coarse grain pyrite, but it comes before the ore. And here we have our nice chunky dolomites. Here we have some silica busting over the top of it, quite clear fracture there. In fact, there's a beautiful breccia texture just in that bit. But then, of course, we have the chalcopyrite busting across all of that with some associated calcite. So as I say to my students, you know, is all the white mineral the same color? Well, no, we've actually got 3 different stages here. That carbonate, that calcite's probably coming in with the chalcopyrite. So it's really interesting to note, I think. This is a nice image as well. Here we're seeing, again, some Urcat Shale, which has been broken over by the very white dolomite. And you can see just where my cursor is here, there's some sort of paler grey stuff. Now that's quartz. And you can see it's overprinting and making its own pathways in a few cases, overprinting the silica, the dolomite. So we often call at Mount Isa silica dolomite, but actually it's dolomite and silica, and the 2 separate events. Now we don't know if that is one fluid that's evolved and dropped out the dolomite, then it fractionates and drops out the silica. I'm not that good a chemist, I'm not sure, but there has been some work on that. But I look at it as 2 events because the dolomite is quite broken. You know, that's not thinking about crystallizing, that was a fairly dolomitized rock. And of course that dolomite is present as you step away from the system, it becomes more layer parallel and it's a bit more replacement. But I'm already getting into too much detail, Jess, sorry. What I like about this image is you can clearly see there is chalcopyrite overprinting the dolomite and the silica. It's clearly veining across them, getting down the edges of those veins and making its own pathways. Fluids tend to go where fluids can go. Now here we're stepping a bit further. Now there is a lot of fine-grained pyrite associated with the Mount Isa system. I'm not going to talk about it here. It's been the subject of endless academic debate because obviously pyrite halos and that kind of thing for exploration is significant. I guess all I'm going to say about it is it's pre-ore. In fact, I'll say a bit more about it because Phil Reiger did some great work on it. But as you can see here is fine-grained pyrite and it's being busted over by this silica dolomite. It's quite clearly breaking across that fine-grained pyrite, and the chalcopyrite is breaking across the silica dolomite. So fine-grained pyrite's early. Now, Phil Reiger did some great work. I guess some of the limitations of early work with isotopes, oh gosh, I didn't think I was going to say that word today, has been if you take a rock and you crush it up, you don't really know what you're getting. Phil did some great targeted isotope work, and essentially, to summarize his very good 3-year PhD, he doesn't think that there's a large scale fine-grained high-low at George Fisher, and we'll extrapolate that to Mount Isa because it's only 20 kilometers away, and formed under conditions open to sulfate. So basically, and it's all in a paper here, which I recommend you have a look at. It's all open file, I believe. It's not sedimentary exhalative pyrite. It formed when the muds were muds. And it basically is part of a diagenetic event sort of thing. It's pyrite that formed relatively close to the seafloor. Is it a sulfur source for later fluids? Absolutely. Is it SEDEX coming out the ground and black smokers and white smokers and stuff? Not according to this data. So I think there's quite a lot of debate about what fine grained pyrite actually means, but that's where I'll leave it because it's pre-ore as far as I'm concerned. There is a good ore deposits hub talk that Phil gave, which covers a lot more detail of that. I'll reference that's a good talk. I guess the other thing that the fine grained pyrite does from a rheological point of view is it's quite hard. And a student, Sam Connell, a few years ago did a really interesting project just looking at the fine grained pyrite and the coarse grained pyrite, which comes in after the fine grained pyrite, but just before the ore. And this picture here illustrates it quite well. Here we have our fine grained pyrite, and here we have some coarse grained pyrite in a vein. And it's essentially the fine grained pyrite's being a bulletproof vest. It's stronger, it's harder. It does break, of course, it's not impermeable, but if I was a fluid, you'd just go around it, you wouldn't bother with it. And as you can see here, these ore shells here, which are broken rock, and the sort of the green outline is where some of the copper ore system is, kind of tends to go around it. So it's kind of, for whatever reason, it has inhibited sort of some of where the copper and the lead zinc has gone, which I think is kind of neat. It's affected the geometry of the ore system, that's for sure. Then as we step further away from the bounding fault, we end up with these rather contorted folded units. Now, a lot of discussions have been had about these, whether these were folded on the sea floor, mineralized and folded. To my mind, this looks a lot like soft sediment deformation. And I would put money on that. But you'll notice here we have sort of the brown sphalerite, we have the galena, and we actually have chalcopyrite. It's pretty common to have galena, sphalerite and chalcopyrite all kind of hanging around at the same kind of time. Something you'll see here as well, it's got a lot of replacement. So this sort of brown is sphalerite replacement, and you see it just comes in there and it stops. It likes this unit and it's gone along here, but it kind of peters out by the time we get up here. So selective replacement is a very important texture at Mount Isa. This is not the texture you would associate with raining sulfides on the seafloor. So it's certainly some form of replacement, I would say. Galena tends to occupy paragenetically fairly late positions. Not 100% sure why that is. I mean, we're talking about a giant ore system here. It obviously didn't form in one go overnight, whether we're seeing evidence of a prolonged mineralization stage or whether the galena is just literally staying in solution a bit longer and sort of forming these like little crack vein fill examples. But again, that's probably a bit too much data info for today. Really important point is that in much of the shale, in this sort of transition zone, the sphalerite and the galena are as infill within the spaces between shale fragments. It's not all layer bounded, it's quite a lot of sort of breccia infill. This is a classic picture. Thanks, Nicole, for forwarding this. This is a classic. Everyone working in Mount Isa in the 80s and 90s would go and get a picture with these. Now, again, I see these rhythmic bands, all of that will be mineralized sphalerite and galena between. I see that as soft sediment deformation. And I guess the example that I have on my shelf at work here in Adelaide, here is a band which is a bit more silicious. These would have been carbonate bearing muds or sort of rocks, which have been a preferential which would be a preferential host rock for mineralizing fluids. I sent this picture to my friend Dave in the UK at Leicester, and he sent me this picture from Leicester University. He said, oh, that's slumping in lake sediments around the Lake District in some units around the Lake District in the UK. And I thought, bloody hell, that texture, particularly up here, is remarkably similar. And this is, I couldn't tell you what age these were, but that's a more carbonate bearing mud. And this is more sort of silicious units. You can see that little rippling, the breaking through there. I'm sure you could talk for days about that if you're a structural geologist or a sedimentologist. But to me, a lot of what we're seeing in this sort of environment, and these are pretty localized folding events, which I put down to sediment. And I just pulled these off the internet. These are sort of more modern sediments, and there's lots of information about how these things can form and what they tell you about the environment of the sediment deposition. I guess starting to get a little bit more about how this thing may have formed. This is something that you see all the time: irregular distribution of stratiform lead zinc ores. So we have some slightly folded units, which we can all agree on. I think I've outlined them there. There's some Urcat Shale units. You can see some more layering over here. And we can all agree that that is busted over by silica dolomite, we'll just call it here. And the important thing here, and this is a Bill Perkins image, is this section here is mineralized. You can actually see it here. There's a discontinuity. Could have been a little fracture, a little quartz field fracture, or just something that stopped the fluid flow here. And you can't do that with sulfide raining down out of the C column. It has to be a replacement. The question of when that replacement took place, whether it was in diagenesis or millions of years later, is I think where the conversation is now for people working on Mount Isa. This is a beautiful image of, this is all sphalerite, the brown. There's some nice coarse grained sphalerite, possibly infill here. And as you see, it's getting towards units that the fluid doesn't like as much, and it's starting to crack in these lovely little fracture patterns. And even over here, the rock sphalerite can't replace it, so it forms these little cracks and veins. And you see this in pretty much every rock you pick up. I like this example because we have silica, or this is probably dolomite, which has abutted a layer, and then the sphalerite here has come in obviously after that has formed. So the rocks had to have been formed and rocky enough to be broken brittly by silica dolomite before it came in. So to my mind, that's evidence it's probably not mud. So partly consolidated rock, or as we'll find later on, I'm pretty confident that it's actually millions of years after that rock formed, but certainly post-deformation. Anyway, I'm starting to trigger myself. Sorry, Jess, I knew this would happen. Here's a nice little vein of sphalerite popping through the rock, finding a bit of carbonate that it likes and sort of popping itself in there. And you see this on every scale, whether it's a thin section here. This is one of Bill Perkins again. Here's all the brown is sphalerite making its way. So nice little alteration up here. And here we see in some other areas, this is just, again, you could pick up any rock in Mount Isa and see this kind of texture. Again, we've got galena forming some texturally fairly late examples. We've actually got fine-grained pyrite that's deformed here. The fine-grained pyrite's been broken over by this coarser-grained pyrite, which again predates the sphalerite, galena, and chalcopyrite. And you can see the sphalerite obviously quite likes this layer, and it's just finding its way where it can go. And it's here you can see it's actually breaking out into the fine-grained pyrite here. So just these ore textures make a very strong case for a replacement origin. And this is probably my finest example of it. Took this photo a few years ago. It's been used a few times now. As you can see, we have irregular distribution of sphalerite within this layer. We have a vein coming across, which has actually got carbonate and silica in it. So it's almost a silica dolomite vein. And this irregular distribution, you can't have sulfides raining out of the C column to have this. And in fact, in this case, even with replacement, these cracks have to have been there. So that rock has to have been consolidated enough to have had cracking and deformation. And as I've said before, mineralization postdates deformation. So I think we're making a fairly strong case for replacement origin. And this is another one of Bill Perkins' slides. Again, not cherry picked, it's just everything shows these textures. Here's some fairly nice sphalerite replacement. And here as the ore fluid has come through, it's actually found a layer that it likes. And it's gone, oh, we'll go in here. Oh, we can't get any further, let's just stop. So there's a discontinuity. And I think these are really cool. And I could show pictures of these all day because they're really clear. And I probably will show a few more. This is a classic. Beautiful, this sort of buff browny color is sphalerite bearing rock. And on this side, it is not sphalerite bearing. And Bill in his work has actually tallied up these two, worked out the displacement. So that displacement must have occurred prior to mineralization. And this side is mineralized and this side is not. So that's lots of good evidence. I will just put a bit of a shout out to Jun Cowan. Jun's actually come up with a name for these discontinuities. He's calling them Perkins discontinuities, and they're actually really common in a lot of systems that are called VMS or remote. Whenever people start talking about, oh no, triggering remobilization, Jun's taken a fairly good line on this, and I would highly recommend anyone who doesn't follow Jun to follow him on LinkedIn. He's written some brilliant articles about structural controls to ore deposits, and there's a case study. He's used Mount Isa as well, which demonstrates that it's not just the copper that's structurally controlled, the lead zinc is as well. So those structures had to be there before the lead zinc came in, right? So this is all good. And just yet another example of sphalerite alteration in the Urcat Shale, just sort of fading out when it either runs out of steam or runs out of sphalerite, or for whatever reason the fluid just, oh, we'll just stop there, maybe got lazy. Anyway. And then it's always nice to talk about something a little bit different. It's interesting, around the edges of the deposit, almost like a halo, you actually get a fair bit of magnetite. Now, not enough magnetite to make it a magnetic exploration target. We'll have a brief look at that. But these are hydrothermal looking magnetites. Some of them form almost like veins. And you can see even in this relatively low tech picture, you can actually see that the magnetite is being taken out by the sphalerite. So it was pre sphalerite and galena, this magnetite, and pretty unusual to make magnetite on the sea floor. You need incredibly reducing conditions. It can happen, I suppose. This is Celsian, which is a barium feldspar, which is quite interesting. You don't see much of that. And I think this is one of Brad's comments, is it's always interesting when you talk about alteration and sort of the pre-ore assemblage, because it's not always well covered in these systems, widely described as SEDEX. And the pre-ore alteration mineralogy at Mount Isa and George Fisher includes magnetite, Celsian, K-feldspar, biotite, apatite, rutile, and monazite. These are not your average seafloor minerals. I don't know that you can make potassium feldspar on the seafloor, but anyway, apparently you can during diagenesis, but I'm not sure about that myself. But anyway, lots of rather hot minerals, put it that way, and there's quite a few of them around. There's lots of pictures of that. And here's some more magnetite. In this particular case study, I think it's from the 3000 ore body. You can see the magnetite crystals. They're not technically infill. They've kind of forced their way in, as magnetite can do, but they're overgrowing the fine-grained pyrite, so they could be taking some of the iron from that. I'm not entirely sure how those formed. It's just a bit of a curiosity. They're there. And we actually did a Nexus workshop on Monday and Tuesday with David Arles and Lee Rankin, and Dave used Mount Isa as a case study for one of the magnetics images. So this was flown, I think, in the late 80s or early 90s. Rick Valenta was involved in this. Unfortunately, that's obviously the town. There's quite a lot of, surface infrastructure. You can't really strip that out of the data, but you can see George Fisher and Mount Isa there. Probably they're the head frames that are sticking up. But what Dave pointed out is you can definitely see some sort of linear features in the basement. There's actually probably one coming down here as well. It could be the Burnborough Fault, which we know is a quite important one in terms of fluid flow. So just a kind of a curiosity that mag is a thing. So the Mount Isa ore system, copper near the bottom, lead zinc near the top. How did it form? The first paper on Mount Isa, Grongis and Schouten, 1937, brilliant paper, my favorite paper. They used the high-tech technology at the time, which was a reflected light microscope. They looked at a lot of rocks, which I think, it can only be encouraged when we're doing research, actually look at the rocks, not just the chemistry. But of course, a lot of people, probably the main model for the lead zinc at Mount Isa is that it was formed on the sea floor at the same time as the rocks were forming. So we'll take a little bit of a look at why this has changed. So the question often comes up, is it epigenetic or is it syngenetic? Questions that I've had myself in the past is why. My PhD was on ophiolites. I spent a lot of time crawling around pillow basalts and seeing lots of little hydrothermal systems in them, but they always had quite a distinct plumbing system. There was a lot of alteration. There was a lot of very unhappy rocks, but you never see any evidence for a lead zinc plumbing system in the rocks. People say it's been destroyed. The tectonism destroyed it, which is convenient. And my main question, this is like you could ask any geologist this: if this blue material, if the lead zinc was there first, a world-class lead zinc deposit, strata-bound or stratiform, if you then overprint it with a world-class copper system, you would hope to expect that you would find a few lumps of this lead zinc system in the copper system, like xenoliths, lumps of lead zinc in the copper system, lumps of stratiform lead zinc, just as a lump in the copper. I've never seen one. Bill Perkins spent years looking for them. We've never found one, which is just fundamentally a crazy thing. Like, you'd have bits of it. It actually zones into each other. You commonly get lead zinc on the edge of the copper. They interfinger, interdigitate, but they don't pump over each other. So I think that's a really important point, which I cannot emphasize enough. So we should start at the beginning with Mount Isa. I know I'm probably going to run over, Jess, I'm afraid, but I've probably got about another 10 minutes of a little bit more of the story of how these things have changed. Mount Isa was discovered by John Campbell Miles in 1923. John had been a prospector and he'd worked down at Broken Hill, so he knew what sort of lead zinc system surface expressions were like. He was a good explorer. That's a great first picture of the racecourse lease, not far from, actually, it's probably just about there actually on the image behind. That's the first wagon of ore. So the story goes that he camped up for the night in the Leichhardt River. In the morning, his donkey had wandered off. He went to find the donkey, and as he got the donkey back, he found these lumps of very dark, heavy material, gossan, basically, of the Mount Isa system, and he recognized it. They sent some samples to Cloncurry. They came back with staggering grades, and of course, the rest is history. I like this picture of the first board of Mount Isa in 1924. That's quite good. They were doing it tough back then. It always makes me laugh when people complain about living in Mount Isa these days, but you can walk down to Woolies in Mount Isa and get a bag of salad. These people were going through some real hardships back then. No aircon, no electricity, had to get your water from the creek. This was real pioneering stuff. And Mount Isa didn't really take off as a mine until 1929, when they extended the railway up from Bullia, perhaps. And that was when it really came home. In the early years of the mine, they were mining lead zinc because it was on the surface. There was always copper around. I've seen plenty of copper minerals on the surface at Mount Isa, but the copper was thought to be minor, whereas the actual lead zinc was the main thing. And it was only in the Second World War that they actually started to really go after the copper, but we'll get to that in a few moments. What does it look like on the surface? These are some of my friend Con's minerals, some cerussite, some pyromorphite, some anglesite. You could walk on the surface today on the mine site and find oxide products. I found some hemimorphite last time I was at George Fisher. This is a piece of the discovery outcrop in the collection at Adelaide University, and you can see little white specks all over it that I've put some rather large arrows on, pointing to the cerussite, lead carbonate. This is just by the Tony White Oval, just up from the Irish Club. There are outcropping examples of mineralized rock in Mount Isa. I won't start the story about the copper grass, but it grows all over it, or metal grass, you could probably say, but there's pretty obvious signs of an ore system where in Mount Isa. The first geological report was done, I think, in 1924, when they described it. I love this picture because that's the original outcrop of Black Star, which is a long gone open cut that outcrop is long gone. The mine only closed a few years ago. I always wondered why they called it Black Star, but of course, when they wanted to mark up their bags, they cut the tin from their jerry cans, and then they daubed some marks on it to give you Black Star ore, so people would know where it had come from. First paper, as we mentioned, used a lot of 250 polished surfaces, 1937, done by some Dutch researchers. Obviously, there was a bit of a pause, but after that, for a few years, not much research going on during the 1940s in Holland. But to summarize, a syngenetic origin for the ore is excluded and an origin by metasomatic replacement is proposed. I think all of us would agree that when it comes to describing actual rocks, they were better at it back then. They really looked at the rocks. They didn't have geochemistry to necessarily distract them into all these other things. I really do feel ore textures tell you most of the story. The other paper is by Blanchard and Hall, two legends of the Mount Isa system. They had a paper in the same edition of Economic Geology, and I think I've enlarged that here. I love this. The replacement clearly took place subsequent to the folding and principal fracturing. So even back in the 30s, they were quite comfortably saying this all came in after this rock had been deformed, which means the rock had to be a rock, right? Surely. So that led to the original epigenetic model. Now, remember, they didn't know much about the copper system at the time. The samples would have been from higher up. So it was really looking at a system where you had lead zinc replacing crushed and sheared shales. And that was the model back in the 30s until the 60s. This is a picture looking from the mine site. The smelter hasn't moved very far. Mount Isa was Australia's largest export income earning mine for a long time. A few other people started sniffing around to try and find some other ore deposits. So Mount Isa looked up strike, and they found Hilton and George Fisher, again from outcropping oxides. It must have been great just popping around doing that sort of exploration. No, it's probably a mine here. And then the 1100 ore body was discovered from surface and then extended and progressed underground. So in the 1970s, one of the great copper ore systems in the world. These are a couple of slides that really just summarize sort of what happened during the 50s and 60s. Now, it's definitely worth noting that during the 1950s and 60s, we had submarines mapping the sea floor, and that's when we first noticed black smokers and white smokers and all that kind of thing. It does not surprise me at all that suddenly everything became black smoker related. There was a lot of work done, particularly, I've got a copy of Stanton's book here behind me and some of these ones. And it all started to go a little bit, this all has to be, if the main evidence for a lot of these syngenetic systems is the fact that the ore is layered. The fact that carbonate rocks are also layered and are subject to a lot of replacement in carbonate replacement systems wasn't so important at the time. But anyway, things started to change in terms of the ideas around Mount Isa based on new data, which is good. That's good, right? So the model then got sort of the replacement model kind of, I should say the epigenetic replacement model kind of got thrown out, and then the sedimentary model kind of came in for lead zinc forming in exhalative ore or a sort of replacement of shallow muds and that kind of thing. And we've all seen this is what we get taught at university, right? This is how these things form. The slight caveat here is they actually seem to think that in some of these models that the copper formed on the seafloor as well. And I don't think anyone believes that now. I think we're fairly comfortable that it's an overprint, but that's the next model, which we'll get to in a few moments. And I think it is relevant that the word SEDEX, which is not one of my favorite terms because it implies exhalation. There's no evidence for exhalation at this system. So, replacement, sure. But the SEDEX model has kind of taken over quite a lot of our thinking in terms of, it's important for exploration, of course, because if you're only looking for one location, then of course you only look for that kind of rock. Sorry, triggering myself again. Because I mean, this is basically what I was taught when I first got to Mount Isa. It was one of these, or rather, not so much one of these, more sort of one of these. And that model's one of Jeff Derrick's great sort of cartoons. But it shows how the diversity of thinking around this system. Then in the 70s and 80s, there was a lot of work done, a lot of PhDs that kind of clashed with each other, and then it kind of consolidated into the sort of overprinting model that we'll look at now. So I guess the model that most of you who've heard of Mount Isa will have heard is that the lead zinc was stratiform, was in the rocks as they formed, was deformed by the events, and then overprinted by the copper. I would put forward that actually it's one system and it all turned up relatively at the same time. But again, that's not the common view. So the current model is, the lead zinc was formed syngenetically or diagenetically and then were deformed, and then silica dolomite happened, and then copper overplaced that, and that's your sort of lightning striking twice model. But then this fellow called Bill Perkins in the 90s, well, Bill was working at Mount Isa before I was born, so much respect to Bill. He's seen probably the geologist who's seen the rocks the most. Bill started to look and say, well, if we draw the lead zinc outline at say 3% and the copper outline, they look like two separate systems. If you actually draw the lower grade halos on, they kind of overlap. And then actually got Bill thinking a great deal. He went to Townsville, did a PhD on Mount Isa, and he came up with a lot of evidence, a lot of ore texture evidence, not so much geochemistry, but a lot of ore texture evidence that said, actually, this is a single system. This doesn't overprint. It actually just goes into each other. It zones. So Bill, I think we have to say, came up with a lot of the things I've been saying. Bill talked about in the 90s, but unfortunately, in the 90s, that wasn't the prevailing view. So actually, Bill had some heckling at conferences and that kind of thing that I think is pretty unfair, frankly, because I think he was presenting a very good story. And I think in geoscience, I think we should definitely keep our minds open to new ideas in that sense. There's a picture of Bill. Bill's still going at the Geological Survey of Queensland. Good on you, Bill, if you ever watch this. And this is he doesn't like me using this quote, but I think it's quite good. And the SEDEX term is the geological equivalent of the cane toad. Once introduced, it's bloody hard to get rid of. There's been a lot of isotope work done to support the SEDEX model. Not a huge fan of isotopes, but we can talk about this later on. But he's right. Once people have posed that idea, you've got to produce a lot of information to then sort of say, actually, no. And unfortunately, ore textures themselves are not widely taught. And because of this, and it's just textures, people can always say, well, actually, I disagree with what you're interpreting. But anyway, just finishing up here. But in terms of the rise of the mine, by the early 2000s, Mount Isa Mines was getting a bit, it was getting a bit bloated on itself. It wasn't being as efficient as it could have been. And then Xstrata Copper bought Mount Isa Mines in 2003, and that's who I used to work for in Mount Isa. And they split the operations into the copper and zinc division, so Xstrata Copper, Xstrata Zinc, and it was kind of like working at two different companies. I think the copper mob always sort of had slightly a bit more hoity because copper was worth a bit more than the zinc, but hopefully that's changed now. And anyway, Xstrata were very good miners. They kept breaking records. Then what year was it? 2013. There was a sort of a merger between Xstrata and Glencore, and then after a few weeks, we were told it was called Xstrata Glencore for a little while, or Glencore Xstrata, and then after a while, we were told just to drop the Xstrata. So it's been a Glencore operation since then. And Glencore, basically let operations be relatively autonomous, and as long as everything's going well and producing production as reported, then Glencore don't get too involved in that sense. Certainly on the day-to-day side of it, I found. Even in the late teens of the 2000s, they were still breaking records underground, most tons, most ore mined per year. So even for most of a 100-year-old system, it's remarkable how many records still being set. The smelter, every few years, they say, we're going to keep the smelter open or close it, but I believe it's still going to stay open. And really, I guess the other thing is, we've only been really looking at the high grade, the sort of 2%, 1% plus. If you take that down to sort of 0.5%, it's a giant system. I'm confident people will be mining at Mount Isa for a very long time, whether they're doing the open stoping method, or sorry, the stoping method that they use at Mount Isa or not, or whether they go for a big multi-commodity pit, which has been proposed back since the 70s, is another question. But I'm confident that there's a lot of ore there, in billions of tons at a lower grade. So essentially, Queensland's got the equivalent of a large porphyry system there. They just need to work out how to mine it efficiently. So I suspect it'll be mined for a long time. And I guess I chuck this in because a month or two doesn't go by without Mount Isa making the news for some reason. I think the last time it was in the news was because there was nowhere to rent there, because there's so many jobs, everything's booming, there weren't many places to rent, and so that's that. I guess from my perspective, I worked at Mount Isa from 2008 to 2015, and then I transitioned to a role here at University of Adelaide, and we did a lot of work on Mount Isa then. I hadn't really studied it up until coming to the university. We've done at least 20 honours projects, 4 PhD projects, master's projects on various topics, not just Mount Isa deposit itself, lots of the Cloncurry IOCGs. But I would say of all of the research we've done, every single bit of data and outcome points to the story that Mount Isa is a carbonate replacement deposit that turned up, after the rocks were deformed. And I guess from that, over 15 years, what do I really think? Well, I think that Bill Perkins got it right. So hats off to Bill. That's my opinion. And I guess part of that, my student Brad Kay has been doing some great work in the last few years. And now that we can actually date things, there's monazite in with the silica dolomite. So we're very comfortable that we can date peak deformation. We can date the silica dolomite, we can date mineralization. And in fact, Brad's dated mineralization at Mount Novitz, which I haven't had time to talk about. It's about 20k south of Mount Isa. We've dated the silica dolomite event down there at about 1515, and we've dated the ore there from sort of about 1480 to 1490. So we're very comfortable with the data that we've got, and you'll find that that's actually going to be published over the next year or so while Brad finishes up his PhD. And of course, this has huge implications for the other copper, lead, zinc marriages up in northwest Queensland. You've got Lady Annie and Lady Loretta. I've never heard a particularly good explanation as to why those two are right next to each other, but I'm suspecting that we're talking about the same sort of thing here. You've got Dugald River, which has a sizable amount of copper in it as well, and the Rosebery Corridor, which is very copper rich, right next to it. And of course, Dugald River is in the Eastern Succession. And when you talk about IOCGs, you have to talk about skarns. And if you talk about skarns, you need to talk about carbonate replacement deposits. So we're really not talking about 1,000 miles apart from each other here. So it really opens up questions for the bigger part of the system and how this actually has an interplay in the mineral system of the Mount Isa area. We're not the only people saying this. I've talked about Phil's work, although again, Phil's work ended up going more with a replacement in the sort of mud model, but that's fine. I'm glad we're having these conversations. There's a great paper from Sam Spinks looking at MacArthur River, where they're showing a carbonate replacement origin there in the muds. And here's a link to, here's an image of Brad's paper in Geoscience Frontiers about the Mount Novit, which has some of the first dating that we've published on some of these Mount Isa events, and I think they're quite significant. And yeah, I guess just to finish up, Brad's got a couple more papers coming out. So this story, we're actually getting some really good data on this now. We're going to date some dikes at George Fisher, which are mineralized. So we can actually date very strongly how these things are going. And there we go. I think on that, Jess, I think I'll finish up, and I apologize for running over time.